Welcome to the General Chemistry 1 class. This section is on gases, focusing on the gas laws. In this lesson, we will express the gas laws in equation form. Gas laws are fundamental laws showing how the following properties of gases are interrelated. The amount in moles, denoted by N, pressure denoted by P, which is the force exerted per unit, and the volume denoted by V, or the space occupied by matter, and temperature denoted by T, which is a measure of hotness or coldness of an object. Let us start by the first law, the Boyle's law. Robert Boyle studied the relationship between the pressure and the volume of gas. To observe this, he used a setup similar to the illustration on the right. Here, a J-shaped tube sealed on one end is filled with trapped gas, a yellow region of the illustration, and mercury, the gray region on the illustration. As you can see on the left image, the gas has a pressure equal to the atmospheric pressure, since the levels of mercury are equal. Consider that the volume of a gas inside is 8 ml. Right image is the pressure is doubled by adding mercury. The volume of the gas reduces by 1/2 of its original volume, which is 4 millimeters. From the observation, Robert Boyle's Boyle's law was established. The law states that for a given amount of a gas at fixed temperature, the pressure exerted by the gas is inversely proportional to its volume. It means that as the pressure increases, the volume decreases. Once the volume increases, the pressure decreases because it is inversely proportional. Introducing a proportionality constant, we have P is equal to K1, K1 as the proportionality constant over V, or PV equals proportional constant, the KL. Okay. Considering two different states, the equation can express as P1, P1 times V1 equals P2 times V2, where P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, and V2 is the final volume. A plot showing the relationship between volume and pressure at a fixed temperature is called an isotherm. Notice that an isotherm has a shape of the hyperbola. Different temperatures have different isotherms. The next gas law is Charles' law. Separate study from the Jacques Charles and Joseph Gay-Lussac focus on the relationship between temperature and volume of a given amount of gas at fixed pressure. In Charles' law, they found out that volume occupied by the gas increases as the temperature increases, while the volume decreases as temperature decreases. It means that there is a direct proportional relationship between the temperature and the volume, and it can be seen on the illustration. The plot showing the relationship between temperature and volume at constant pressure, called an isobar, is linear. Different isobars give different linear plots, with different slopes. However, the isobars project to a constant value of temperature at zero volume. This temperature is called the absolute zero of temperature. It is equal to zero on the Kelvin scale, which is equal to negative 273.15 degrees Celsius on the Celsius scale, converting the temperature from Celsius scale to Kelvin scale, where absolute temperature is given by in T in Kelvin is equals to temperature in Celsius plus 273.15. The absolute zero or 0 degree Kelvin is considered to be the lowest possible temperature that can be attained. The observed relationship between the temperature and the volume of gas is known as Charles' law, which states that for a given amount of gas at fixed pressure, the volume of the gas is directly proportional to its absolute temperature. Don't forget the keyword, directly proportional. Volume and temperature are directly proportional. Introducing a proportionality constant, excuse me, the K2. The equation becomes V is equal to K2 times T or V divided by T equals K2. Considering the two different states, that equation can be expressed as V1 divided by T1 equals V2 divided by T2, where V1 is the initial volume, T1 is the initial temperature, V2 the final volume, and the T2 the final temperature. Inclusive to the Charles law is the relationship between the temperature and pressure, and it can be seen on the illustration. For a given amount of gas at constant volume, the pressure is directly proportional to its absolute temperature. Again, directly proportional. Pressure and temperature are directly proportional. Introducing a proportionality constant, the K3. The equation is given by P is equal to K3 times T or P divided by T equals K3. Considering the two different states, the equation can be expressed as P1 divided by T1 equals P2 equals T2, where P1 is the initial volume, P1 is the initial pressure, and T1 is the initial temperature, P2 the final pressure, and T2 the final temperature. Just like the temperature and volume plot, a temperature pressure plot, which is called as the isochord, is also linear. Different isochord for a gas differ on the slope, but can also be projected to zero pressure or T is equal to 0. Lastly, we have the Avogadro's law, proposed by Amadeo Avogadro, hypothesized that equal volumes of different gases subjected at the same pressure and temperature have equal quantities of atoms or molecules. This hypothesis, which is known as Amadeo Avogadro's law or Avogadro's law, can be also stated as follows. At constant temperature and pressure, the volume occupied by a gas is directly proportional to its amount in moles. And it can be mathematically expressed in V inversely proportional to N. Introducing a proportionality constant K4, where we have V is equal to K4 times N, or V divided by N K4 is equal to K4. Considering two different states, the equation can be expressed as V1 divided by N1 equals V2 divided by N2, where V1 is the initial volume and N1 is the initial amount in moles. V2 is the final volume and N2 is the final amount in moles. The Avogadro's law enables us to determine the molar volume of gases. Molar volume, denoted by V bar or the Vn, is the volume occupied by 1 mole of a gas. This is also referred to the proportionality constant, or the K4. At the standard temperature and pressure, or STP, in which the temperature is 273.15 Kelvin or 0 degrees Celsius and pressure is 1 atm or atmospheric pressure, gases have molar volume of approximately 22.4 liters per mole. On the other hand, on the standard ambient temperature and pressure, or SATP, in which the temperature is 298.15 Kelvin or 25 degrees Celsius and pressure is 1 bar. The molar volume equals 24.8 liters per mole. In one of our future lessons, we will find out how we can arrive at these molar volume values. To summarize, gas laws show the interrelationship of the amount, pressure, volume, and temperature of gases. Boyle's law illustrates the inverse proportionality of the pressure and volume for a given amount of gas at constant temperature. Charles' law states or illustrates that direct proportional there is direct proportionality of volume and temperature of a given amount of gas at constant pressure, as well as the direct proportionality of pressure and temperature of a given amount of gas at constant volume. Lastly, Amadeo Avogadro, or the Avogadro's law, illustrates the direct proportionality of the volume and amount of gas at constant temperature and pressure. We have our references or the bibliography for further readings. Thank you.